the class. So any of you can, if not, uh, if you're not able to participate to an online lecture, you can always give a look to the recorded lecture that you will find on my YouTube channel, for which I will provide you a link on the Moodle class homepage. First of all, I would like to ask you if you have any questions and if you were able to connect to the Moodle site, and if everything is clear on this page, and if you can connect and download the material. Typically on the Moodle page, you will have the overheads, what I'm presenting day by day. So this lecture that I'm giving today, you will find it on my YouTube channel. The playlist is the name of the class, so Modeling Control of Environmental Systems. For me, it is MCES, and then the date of the lecture, the date on which the lecture is being held. So for today's, you will find a recording whose title is MCES, Modeling Control of Environmental System, the date of today, that is 05/10 to 2021. So Modeling Control MCES 05/10/21. It is the title of today's lecture. For day by day, you will find every lecture with the name of the class and the date. So we were saying modeling control, modulus, paradigm, description, control, that is monitoring, observation, appraisal, but also management, meaning interfering with the working of the system, but modeling and control of what? Of environmental systems. Environmental systems, we spend quite some lectures in describing and defining what we mean by this concept. Environmental system, it is a conceptual wraparound word in which we include a lot of systems, in particular the systems environmental engineers are focused on, so natural systems, systems for which the natural aspects are the one that engineer is interested on. Environmental system, environment has to do with ecology. You may know that the word ecology comes from the Greek word oikos, logos. Oikos means environment, or if you want, in an extended sense, it means house, home. Logos is the study of our home. So ecology is the science what studies our home. And by extension, this is science what is studying the environment. In a large meaning, it is our home. Ecology is a similar word to economy. Economy, oikos, nomos, oikos again, environment, home, house. Nomos is the set of rules that govern our houses, our homes. So oikos, logos, study of environment, oikos, nomos, study of laws that govern the environment. In very general term, this is the topic of this class. So we are talking about the concept of environment. So we may start by giving some more sound and clear definition of this concept. What we may define environment is, as the European Council proposed in 1973, the set of elements that in the complexity of the relationships, of the relations, constitute the framework, the habitat, and the conditions of human life, which are in reality or what are perceived. So again, some interesting concepts, some interesting words. Let's give a look. Set of elements. So we immediately recognize that the environment is made up of a series of well-distinguished elements but are somehow complex, and we will discuss. We will spend a lot of time in trying to give a definition of the term complexity. Complexity, again, is a Latin word coming from complexum. Complexum means to embrace. So complexity refers to the fact that this kind of models description embraces different hierarchical levels. These elements are linked in a complex way by a set of relationships that constitute what? The framework, or you may say the habitat in ecological terms, and the condition of human life. So you see that the definition of environment is quite an anthropogenical perspective. So we look at the framework and the conditions that favor or foster human life. And the final very important concept is that of being in reality, or what are perceived, meaning, again, this is a very anthropogenic and subjective concept, but what we understand since the beginning, that we will not pretend to give the description of a reality of things, but in particular, instead, we will be more focused on the perception that humans feel about the environment. So again, the concept of human life perceiving the condition of the environment are key concepts in order to build up a useful model for describing ecosystems. What we will discuss during this class, I give you a short and at all not exhausting list of concepts, introductions, so what we are doing today. Then we will spend some time in describing and discussing the stages of a modeling procedure. You will see that we will enumerate at least 8 fundamental steps in building an ecological model, and we will describe each of these stages or each of these steps. Then we will introduce model conceptualization and the concept of model complexity. We'll give you some hints or some ideas on how to measure the model complexity and the complexity of the ecological or environmental system we're going to study. Then we will go into the hard part and the hard science of the story. We will introduce physical, chemical, and biological processes. As you will see, if you look at the Moodle page of the class, one of the texts of reference is my book that is whose title is Ecological Processes. So what are ecological processes? Are physical, more specifically chemical, but what is new in particular for the engineers are the biological processes. We will introduce the concept of limiting factors, as we will say several times in this class. Unlimited growth or unlimited condition are ecological nonsense, meaning that in the reality, natural systems are limited. So are limited in several senses, and we will try to make this clear during this class. So we will discuss a very important concept of limitation, and what is limiting the growth in particular, or what is limiting the possibility of environmental or ecological systems to develop. Then we will introduce a set of models, in particular metabolic models. We'll give a very short introduction of the way in which models of energy flows may be employed in order to build a description of ecological systems. Then we will give you an introduction to or an outline onto ecotoxicological processes, for which I think you have already seen some examples during your career, your student career. Then we will introduce some specific models, in particular trophic networks models. That is my today a standard de facto, in which trophic. Trophos means food. So we will discuss models in which we will describe how food networks are may be employed to describe ecological systems. Then we will discuss some specific concepts like that of climate change or acidification. Okay, we will not go too much in depth, but it should be clear to you that climate change, acidification, and so on are all effects or processes that are very relevant when you deal with ecological or environmental systems. It is clear to everybody that climate change, it is an issue today. Then we will introduce a class of very important models that is distributed parameters models. So we will give you an introduction on how to employ GIS, or Geographical Information Systems, in order to build a model of particular ecosystems. In particular, we will introduce MONERIS, that stands for Modeling Nutrient Emissions into River System. That is a model of a very large river ecosystem, river catchments. If we will have time, we will introduce some wastewater treatment plants models. We will have a seminar with Luca Vezzaro concerning stormwater runoff. That is an important aspect related to urban system management. You may imagine that stormwater, it is an issue in urban systems. I have stated mod flow, but I don't think we will have time this year to describe groundwater models like mod flow. We will also not discuss meteorological and atmospheric models because it is too complex. Instead, we shall introduce a set of models that may be new to you, that is the models linked to ecosystem services and various models employed for environmental impact assessment. So if you are not familiar with the concept of ecosystem services, don't worry, because you will have an entire lecture on ecosystem services. But in very short, ecosystem services is a way of putting economical label onto the various aspects of ecological system that we may think are important. So giving economical labeling provides already a ranking of the different services provided by ecosystems in terms of monetary units. So I'm thinking about euros or dollars, of course. Okay, this is a printout of the calendar of the class. You can download it from the model page of the class. You will see we'll have an introduction. We are here to the introduction, generalities about models. Then on next Thursday, we will discuss Monday, Tuesday, Wednesday, Thursday, yes, this Thursday, the next lecture, we will discuss research and management models. We will introduce two philosophical, or if you want, epistemological concepts of relevance, that are holism and reductionism, tied to perspective of a biologist or ecologist when building a description, a mathematical description of environmental systems. Then from next week, we will start going a little bit more into the details. We will have a discussion of the history of evolutions, because it is quite important for us to understand how things were being developed on our planet. So we know that our planet is one of a few planets on which life exists. Of course, I am quite certain that life exists in several other planets in our universe, but I am as well quite certain that it will not be possible to have any information about these other systems. because there are physical limitations. Think, for example, of the speed of light, what is a physical limitation, but we cannot overcome. This means that signals, at least to our understanding today, the maximum speed at which signals may propagate in our universe is the speed of light. So this gives immediately some kind of limitation in terms of how far we may imagine to go in our observation of the universe. This is a very short discussion, but if you want, we may deepen the concept because it is quite interesting. But by some estimations, we are quite certain that life exists elsewhere in our universe, and we are also as well certain, quite certain, that we will never get in contact with these our different living systems. But it is quite interesting to study how the evolution uh, played on our planet in order to bring us from the 4.5 billion years ago, what we call the primeval soup, il brodo primordiale. How did we came from 4.5 billion years ago to the today's life? In order to understand this, we shall make a very short description of the history of evolution, and we will introduce the concept of epigenetics of Gaia. What is Gaia? Gaia, it is classically in Greeks, pantheon, the Greek pantheon, Gaia was the deess, the goddess that represented the earth. So Gaia is a view of the earth as an entire ecosystem, but was introduced by James Lovelock in the late 60s of the last century, in which Lovelock tried to introduce the concept that we may look at our planet as a unique, gigantic ecosystem that has colonized the surface of the planet. In more general terms, modern ecologists say that life is an ongoing phenomenon that is pervading all our universe, probably, and for which we have a specific realization in particular spots, like, for example, the Earth. Our Earth is one of the spots. So we'll discuss the history and the epigenetics of Gaia. We will introduce modeling elements. Then we will have a discussion about model types, how to select a model, how to build a model. So we will introduce the modeling procedure, as I already discussed. In particular, we will introduce the procedure of building conceptual diagrams of ecosystems model. And then we will introduce the concept of complexity, giving you a way of measuring the complexity of ecosystem, but also the complexity of the model that you are using, you're employing for describing your ecosystems. Then we will finish the modeling procedure by the last step, that is verification. And then we will switch to the very important steps of sensitivity analysis, parameter estimation, the so-called calibration. Then we will discuss about model constraint and validation of mathematical models. And we will have a final lecture, final introductory lecture, that is called the equilibrium between spheres, in which I will try to list and enumerate the various processes you may or may not know already that involve exchanges between the various parts of space-times in which the living process takes place. And when I talk about various parts of the space-times, I'm thinking about the atmosphere, the hydrosphere, the lithosphere, and the biosphere as well. So this is why we call the exchanges equilibrium of exchanges between the different spheres. This finishes the first 3 weeks of the first months of introduction, and then we will go into the details of the processes. We will start discussing physical processes, in particular ecotoxicological processes, processes like absorption of the balance, transport and chemical reaction models, and so on. These are all things that I assume you already know. What we are doing here is that we are recasting these things in such a way so that you can build a consistent mathematical description of these processes. Then we will discuss with some specificity settling and resuspension, that are the two relevant ecological processes describing interaction between a water column and the bottom part of water column, the sediment. And you, as environmental engineer, you may already have an idea of how important these interactions are, because of course sediments are a sink recording the history of what is going on to a water system, to a water column. So we will discuss settling, but is the movement of material from water column down onto the sediment, and resuspension, that is the other way around process. So the movement of material from the sediment toward the water column. We will then discuss energetical factors like solar radiation and the temperature, and then we will introduce the nitrogen cycle. That is already something that you should know. You may recall that nitrogen and phosphorus are the main nourritor, I will say nourritor, the main food for living systems. Our life is largely based on nitrogen, phosphorus. Our life, as we see it or understand it in our planet, is largely based on nitrogen and phosphorus exchanges, as well as carbon, hydrogen, and so on. But the fundamental one, as we will see, are nitrogen and phosphorus for several reasons. We'll spend a lot of time in discussing the stoichiometry of biochemical reaction, biochemical exchanges. And in this, it will become clear that nitrogen and phosphorus play a very important role. It is relevant to underpin now the fact that we will give an important focus onto water ecosystem for several reasons. The first reason is that I am an expert of water ecosystem, so I'm an expert in modeling water bodies, lakes, sea, coastal zones, rivers, and so on. And the second, not so important, not so subjective reasons, is that, as we will try to explain during the class, life has been developing in water, finally, and life is impossible without water. Water is a very strange substance. Okay, I understand that for you what I call water strange substance may sound a little bit weird, but water has a quite peculiar characteristic. We may call this substance hydrogen oxide, or dihydrogen oxide, as you prefer. But this molecule has very, very, very peculiar characteristics. For example, but we will discuss in depth several of these characteristics. For example, the fact that solid water is less dense than dense water, but liquid water. Solid water is less dense than liquid water. This means that ice floats on liquid water, and this makes a very important condition. We see several examples of that. The other important fact is, as we will say several times during the class, water is the most diffuse solvent, and it is the medium through which all the materials, and I'm thinking about food, again, nitrogen, phosphorus, but also wastes from biological activities are transported into the ecosystem and in and out and through different ecosystems. Then, after this month and a half, you will start working with Alberto Barause, and you will have several lectures on MATLAB. Why this? Because one of the scope of this class is that of teaching you how to build a mathematical model of a living system. So with Alberto, with Professor Alberto Barause, that is an environmental engineer's background, but now he is an ecologist, that is working to the biology department, will teach you how you may build up a description of a real ecological system onto the MATLAB mathematical environment. I don't know how many of you are already familiar with MATLAB. Don't worry, we assume that you are not familiar at all. So you will have these two introductory lectures, and then you will have several other lectures by the end of the class, a couple of lectures, so in total 4 lectures. There are seminars if you want on MATLAB, or if you want, these are lab works. So I will provide you with a virtual machine on which you may run MATLAB. If you go onto the Moodle webpage of a class, you will see also that the University of Padua provides a license of a MATLAB software, so you can download MATLAB and install it onto your computer so that you can play at home with MATLAB. As I was saying, this is important because one of the objectives of the class is that of making the students capable of building a mathematical model in the calculating environment of MATLAB. In particular, I think we were discussing with Alberto Barause last week about which particular case studies to propose. What I think we traditionally proposed a model of the Piovego River. The Piovego River, you can see it outside of your classroom windows because it is the river that is contorning of the university, come si chiamano i dipartimenti di ingegneria, via Marzolo and via Gradenigo, via Luzzati. So Piovego is this very nice small river in which you have all the nice bars and in which you take lunch during your student life. I was saying that up to last years we used Piovego, so we had some data on the Piovego River, in particular nitrogen and phosphorus concentration, discharges, and so on. And we subdivided the class of modeling and control of environmental systems into groups, and each group was supposed to build a mathematical model of the Piovego River. You are very lucky because after 4 or 5 years of building models of the Piovego River, we are very bored of hearing always the same story. So from this year on, we will change the subject, and we will propose you a data set on the Barene. The Barene, I think for the Italian students, well known, are a very important part of the Lagoon of Venice, are intertidal ecosystems. So these are systems that for half of their time they are submerged by the seawater, and half of their time they are emerging. These ecosystems are very, very important in terms of diversity, provision of ecological services, ecosystem services like water cleaning, or providing food for other species and so on, providing habitats and so on. This is why the barine, I think in English, are so important, and this is why you environmental engineers will be charged this year of building a model about one intertidal system we were working on last years, but is the Palude dei Laghi, in the northern part of the Laguna of Venice, on which we had a very important and interesting and at the edge of science project Vimine, that lasted 4 years, and for which we had several prizes, I would say several recognitions by the scientific community. And but it's very interesting for the reasons I told you, because the marine sustains by the biodiversity, provide habitats, provide food for several systems, and clean the water, and so on. Then, starting from November, 23rd of November, we will give an introduction of distributed parameters modeling. So this is the GIS or Moneris models. I give you an example of a catchment scale model of nutrient loads into river system. In particular, the model I will present, we will discuss, is a model of the Po River. The Po River is one of the largest rivers, I think the third or fourth largest rivers in Europe. Hydraulically speaking, is a monster. Po River is a monster but it's characterized by an average discharge of 1,500 and something cubic meters per second. And with an average in the last 60 years or something like that. So this tells you, at least by comparison to our system, how large is this river. And the catchment of the Po River, that is 70,000 square kilometers, is a very relevant area in the Italian surface, which we have one of the largest gross, how to say, PIL, gross domestic product generating industries. So it is an industrial area, but it is also an agricultural area. So we have secondary and primary and secondary sectors, but it is also an area that is very relevant from the tertiary sectors, especially because it holds 17, probably today we are also around 18, 19 millions of Italians are living in the catchment area of the Po River. So you may imagine that with almost 20 millions of people, Italian people, produce some environmental ecological impact on the catchment, and this is reflected on the water quality, and in cascade this is reflected on the water quality of the coastal area receiving the water of the Po River. The coastal area receiving water of the Po River is the Northern Adriatic Sea. Just to give you some numbers, very short, very briefly, the Northern Adriatic Sea provides more or less 20% of the fishery catch in Italian fishery industry. So it is 1/5 of all of the fisheries in Italy is produced in this area. And why this area is so productive? Exactly because there is the Po River that is discharging a large quantity of nitrogen and phosphorus in the Northern Adriatic, so that this gives rise to a relevant, important production of important primary production, what means we are thinking about algae, phytoplankton, and on the trophic chain, on behalf of the trophic chain, this brings up to fishes and then birds and then to human communities. Okay, again, in the beginning of November, we will introduce metabolic models, but this is a very general abstraction way of including some general principles like the principle of energy conservation and the principle of fixed stoichiometry, as we will see, in building a model of energy flows. And this is one very consistent and robust way of building a mathematical model of living system. Then from the week after, we will go into some more details on the various processes. In particular, we will discuss some ecological processes, light extinction, photosynthesis, and primary production. Photosynthesis is the process that converts light and raw nutrients into biological elements, into biomass. And then we will introduce more in detail the concept of limitation due to availability of light and nutrients to growth. We introduce the concept of grazing. We'll discuss phosphorus cycle. We will introduce the effects of temperature on algal growth. Again, this is a limiting effect. Then we will have a stop lecture of 9th November, sorry, December 9th will not be held because I have a Congress, I'm not here. Then you will have two final sessions of laboratory, MATLAB, during the third week of December. And then you will have the first very interesting seminar by Luca Vezzaro that will introduce you urban runoff and the problems linked to urban runoff. Luca Vezzaro is an environmental engineer that graduated in Padua several years ago and now is working for the municipality of Copenhagen in Denmark, and is working exactly managing urban runoff. And urban runoff, as you may know already, as environmental engineers, is important because urban runoff is a way of moving a lot of nutrients, again, nitrogen and phosphorus, from paved areas or urbanized areas into the receiving water bodies, so the receiving ecosystems. Then the last lecture of the class will be on January 13th, in which Alberto or me, I don't know already, I don't know yet, will discuss trophic networks models, what is and the concept of network analysis, the tools of network analysis. This is a very abstract and high level way of describing the interaction between the complex interactions between the various ecosystems elements, and we describe the interaction by following the fate of foods with. Okay, so this is a very brief and general introduction. Do you have any questions? Any doubts? I was not sufficiently clear. You don't have doubts. Fantastic. So I'm expecting very collaborative students from you. You are understanding. Or I'm very well in explaining. These are the two way of seeing everything. Okay, so let's go on with the introduction. Give me half an hour more to finish this introductory lecture, in which I will introduce some generalities concerning models. So I shall now introduce some very trivial concepts. The first idea or the first concept you are faced with when you are thinking or you are conceptualizing an ecological model is the problem of scales. When I'm thinking about scales, I'm thinking about temporal and spatial scales. You will see that scales are appearing here and there, almost everywhere in the procedure of building ecological models. Defining scales is close to the concept of defining the complexity of the model, or if you want the resolution of your model, or if you want the data needs needed by your model for being calibrated in a consistent way. So the first aspect of the system you want to describe, you shall take into consideration are the scales, the temporally and spatial scales you should assume when building the description of your systems. Spatial scales mean kilometers, centimeters, hectares, and so on. Some processes are well described on specific scales. For example, chemical processes are well described on the scales of centimeters in terms of spatial scales, and on the scales of minutes or seconds in the temporal scale, while, for example, other processes like landscape processes need much larger spatial and temporal scales. I'm thinking about seasons for temporal scales, months, seasons, years, and hectares or square kilometers for spatial scales, and so on. We will see several examples of this scaling or this definition of complexity of resolution of your model when we will introduce physical process models. We will use very high resolution temporal scales, meaning we will discuss about seconds, minutes, or maybe hours or days. And we will introduce as well very relevant, very high definition spatial scales, meaning centimeters or meters. When we will instead describe, for example, landscape process, like for example, the process of nutrient elimination on a large catchment or on a large river catchment systems, then we will change our scales into years, seasons, or decennial, decadal, or centuries, and we will change our spatial scales on the scale of square kilometers and so on. The second important concept the modeler or the environmental engineer should keep clear in his mind is that the model, of course, is not the reality. The model is just a rough approximation of some aspects of reality. Which aspects? Exactly those aspects the environmental engineers feels are relevant for the scope of its application. So you shall never pretend to be the model that describes in its entire complexity of all the reality of an environmental system or an ecological system. Instead, you will see one of the relevant part of the force of environmental engineer is that of cutting the edges or selecting those parts of those processes that you feel as an expert need to be modeled more in detail according to the scope of your model. You will see that also the scope of your model is an important determinant in the way you are going to build your model, so in the conceptualization phase. So you will conceptualize your model according to why you are building your model. Again, this is quite trivial, banal phrase as the model is not reality, of course, but it is important to keep in mind this aspect because very often or quite often it happens that modelers are so happy about their newborn model, children model. They are so happy that sometimes they forget that the model is just a sketch, a caricature, if you want, of a reality, so that many important relevant processes may not be included into the model. And this brings to a fact that sometimes the modelers are so convinced about the goodness of their model that they trust their model and they are very surprised when they notice or when they observe that nature is not behaving as they are expecting it to behave. So then you have two choices. The first one, you say, okay, my model is wrong. And the other choice is, okay, no, the nature is wrong, is not following my model. Of course, the second chance is wrong. So the modeler should go a step back and include some more aspects and verify that the model is really behaving as the model expected it to behave. Then we shall introduce several model types. We will have several discussions about model types. The first important distinction is, if you want, an epistemological, mathematical, philosophical distinction, is that between deterministic and stochastic model. Deterministic models are the so-called Cartesian models, so are models for which the input determines in a deterministic way the output. and this is the dream of all the modelers. For example, physical models are built in this way, are mostly deterministic models. This happened until last centuries, when we had, in the beginning of the 20th centuries, quantum mechanics. But on the beginning of the 21st century, quantum mechanics, sorry, on the beginning of the 21st century, yes, the 20th century, sorry, the beginning of 1900s, quantum mechanics, in which physicists had to accept that even physical models are not necessarily deterministic. There is some kind of randomness or stochasticity. So from quantum mechanics, stochastic processes became very relevant, very important, and they have been included into a theory. So if you look at the postulates building up quantum mechanics, one of the postulates you had, for example, the Heisenberg and, principle of indetermination. It is a clear example of how stochasticity may change your perspective, making deterministic modeling not applicable, not always applicable. Then the other important distinction is that between distributed and aggregated parameters model. This has to do, again, with the choice of scaling. A distributed parameter models, is a model in which your parameters change values according to different times and places in spaces. So you have parameters that change in times and space. While into aggregated parameters modeling, you try to cluster as much as you can all the parameters into a single point in the space-time. And these are aggregated parameters. Of course, the engineer and the mathematical model would like to have aggregated parameters because it is much easier in terms also of computational requirements. But as we will see with several examples, aggregated parameters is not always an acceptable choice, in particular if you are describing processes or ecological processes whose scales are very reduced in terms of, for example, small spatial scales, centimeters, millimeters, or small temporal scales, seconds or fraction of seconds, and so on. There are several examples of mathematical models. Of course, we are not going to the details of all these models, but have been listed here. Tailoring for building dresses, or wind tunnels that are models one-to-one in terms of dimensions, 1 meter to 1 meter, in which you try to describe the effect of wind onto the scaffold of cars, for example, vehicles. Then weather forecasts are very interesting models, very interesting, especially because clear examples of how complex natural systems may be very difficult to describe. In particular, you may know that weather forecast models provide realistic forecasts up to some days, 3, 4, 5 days, and then after this timing, they become dramatically not precise. And so we make weather forecast models, very approximate models. Flight simulator, I include this in this list because these are very interesting examples of mathematical models that have been turned on onto commercial systems, like, for example, flight simulators. Not only for gaming, of course, but flight simulators are also used and employed for preparing pilots. Econometric models that try to make economic forecasts. or physical lagoon models. For example, we have, you may know the history of Moses in the Lagoon of Venice, le dighe mobili that close the Lagoon of Venice from the high tides in order to preserve the city of Venice. When how do you say, when designing the Moses system, they employed a model of the Lagoon of Venice. It was a physical model, but you may observe it in Volta Barozzo, where there is a CNR big building in which there is a 1 to 10 Lagoon of Venice physical model. And by this model, for example, this is an example model of how a physical model may be employed to verify the working of mathematical model. Okay, in very general terms, we shall introduce the modeling procedure by this schema. You know, you will see during this class, I try always to make some kind of schematization. I'm a schematic because I'm a physicist, so I'm trying to schematize my reasoning in drawings of boxes and arrows and flows connecting boxes. So the procedure of modeling may be schematized by this drawing. For example, you start by formulating your hypothesis. So this is the starting point. For example, a lot of nutrients may generate the problems of eutrophication. This is an hypothesis. When I build a model for describing or trying to describe or parameterize the hypothesis, the model may say, for example, thought some quantity of nitrogen phosphorus may result in a quantity of primary production, algae. So you construct your model. This is the second step. And this is the point at which you make validity tests. For example, you verify that the model is behaving exactly as the model expects it to behave. If this is not the case, then the model should come back and try to understand where he put the wrong sign or he made an error in formalizing in mathematical terms his understanding of the system. If a model is validated, if a model is not validated by this validity test, when you go back to the modeling, to the construction of the model, so you adjust, you rearrange your model in order to pass the validity testings. Once the model is validated, this is point 4, then it is the time in which you're ready to apply your model to real ecosystems. So in general, what you do, you start by an observation of a real ecosystem, for example, a lake. You realize that if you have important nutrient loads onto this lake, then as a consequence, you have eutrophication, this algal bloom. Algal bloom may cause, for example, nuisance, production of bad smells from the lake because there is organic matter that is rotting, is wasting. Okay, when once your model is validated, you are ready to apply this model to a different ecosystem. Different from what? Different from the system you started thinking on when you were building your model. So for example, in the case of a eutrophication model for a lake, you shall employ your validated model onto a different lake, but manifest or shows the same problem of eutrophication of algal bloom, for example. Once you have applied your model to some real ecosystem, so we are here, when you're ready to get back to verify if the hypothesis from which you started, for example, a lot of nutrients increases the risk of eutrophication, are verified or not. If not, then this is the point at which you are ready to improve the model, for example, by redefining some underlying assumptions. And then, as you will see in a cyclic procedure, you will refine your description more and more Only when you consider your model complete, then you are ready to employ this object to verify and sorry, you are ready to employ this tool in order to verify and deepen your understanding. So this means building new theoretical formulations. So with a complete model, you have a tool that may help you in build a theoretical formulations of very general processes. So this is just to explain you which is the role of models in scientific research nowadays. We started with a lot of blah blah by saying that natural systems are complex systems. We started by saying that the model is not the reality. So we say we are aware of the fact that the model is not describing all the aspects of a real system, but instead we recognize the fact that the model is useful in describing some relevant aspects of a real system. Relevant to whom? Relevant to you, that are the scientists that is building this tool for deepening your theoretical understanding of the system. So in this perspective, the model becomes a scientific inquiry tool, a tool for deepening your understanding of the theory of living systems. So this is a condition, as we will try to explain you several times during this class. This is a condition that is unavoidable, especially when you deal with natural systems, but are complex systems, systems that react in a non-trivial way to external stimulation. So when you look at environmental systems or natural systems, you are not looking at a simple pendulum, for example, for which the description, the theoretical description is quite simple. Once you have identified the way of describing forces and the law of motions when you have done. In ecological modeling or in ecological theory, ecosystem theories, there are not such uh, general theoretical abstractions. Instead, you are always faced with the fact that your knowledge is limited by several things, by several aspects. Is limited by your knowledge of a system, by the complexity of a system, by the fact that the real systems and natural systems are living systems, by the fact that life provides unexpected responses to external stimulation, so that um, when you deal with natural systems, you have to accept the fact that you may employ these mathematical tools that are mathematical models in order to verify your hypothesis. This is the sense of this schema. You build a mathematical model in order to verify your theoretical hypothesis and then to improve your theoretical understanding of the system. Now let's finish this lecture by giving you some more examples of different model types. We may subdivide model types into two very general categories: physical models and mathematical models. Physical models on their turn may be subdivided into true scale models or distorted scale models. True scale model, the example of the Laguna of Venice, um, sorry, the example of a wind tunnel is a true scale model in which you put your car and you verify how air moves around the scaffold of your car. Distorted model, the example is the Laguna of Venice in the Volta Barozzo Capannone, in which you have a 1 to 10, 1 meter corresponding to 10-meter description of the Laguna of Venice. These are physical models. Mathematical models, on the contrary, you have more and more and more different types of mathematical models. First distinction we have already seen is statistical and stochastic model. So sometime if you are lucky, you may employ some kind of statistics, for example, average discharges, average speeds, and so on. Or you may introduce some kind of stochastic description, so introducing some kind of random perturbation to your mathematical model. Okay, I'm very vague here, but by following the classes, you will see that we introduce some example, be more and more precise on this. Deterministic is another type of model that is opposed to stochastic or statistical. Steady state models are models for which you may identify at least one state variable but is not varying in time. So a steady state model is a model for which you have a quantity that is constant in time, steady. Dynamic model is the contrary of a steady state model. Structural dynamic model are very complex models for which the structure of your system, the structure of your system is changing in time. Meaning that some aspects may come into play after a certain moment into your model, so you have to change the structure of your system by, for example, inserting a new species or a new flow or a new process of exchange with the structural dynamic model. For example, a new species arrives, invasive alien species, or distributed and aggregated parameters model that has to do with the spatial and the time resolution of your models. So these are four different model types. Physical models, some more examples. A ship may be a smaller or larger physical copy of an object. A ship customarily is built in a smaller dimension, a smaller physical copy, in order to study the effect of, for example, water flows on the hull of the ship. You may remember Bohr's atom model is one another example of a physical model that was introduced in the late of the 19th century and beginning of the 20th century for describing atoms. There are some more natural focused models like the microcosms. The model is biosphere 2, for example, that is a model built by NASA in the desert of Nevada because they have a lot of space, so they have selected a portion of space that was insulated by a glass cover and in which they have tried to reproduce all the processes that were relevant in governing the growth and of growth, for example, of food. This was classically an experiment, or if you want, a test, a task carried out by NASA because, as you can imagine, relevance for spatial explorations. Then you have batch reactors, which is a physical model in which batch reactor is a container in which you maintain all the condition, physical, chemical condition constant, so that you can study the development of several processes. In particular, batch reactors are the environment in which biologists study, for example, bacterial growth. Dams and lagoons are also subjects of physical models. Topographic models are another example of very interesting or specific important modeling approaches. Topographic models are based on geographical maps that give different representation but are different according to the different purposes. For example, topographical models may be the models of streets or roads connecting different points of a territory. The model contains the element of interest, for example, road map We have included all the streets, but of course not the vehicles, because if you include the vehicles into your roadmap, your model after a few seconds will not be updated anymore. So you have to change your model. So this is a good example to understand why not all aspects of a reality shall be included into a model. You shall include all those aspects that are bad to stay and that are relevant according to the scope of your model. Mathematical models are the tools, as we introduced you, that allows you to go from analysis of real situation to synthesis. For example, an equation may describe the process of grazing. The process of grazing, in Italian, è brucare. It is the process of feeding of high level, high hierarchical level animals or organisms. The process of grazing, but is a result of a very complex and ubiquitous, a very complex set series of processes may be summarized on a single equation. The point is that mathematical models allows us to deepen our understanding of the process as according to as I was trying to describe you with this schema. Okay. And then an important distinction is that including management models. Management has to do with process management. For example, the process of baggage claim in an airport may be described by a management model. Just to give you an example, one of the largest airports in, I think, was Detroit in the United States, they several decades ago they were building baggage claim models. They made an error by exchanging a plus with a minus sign, and then all the airport was completely lost because of the baggages were not able to be delivered, so they had to close the airport for a week and so on. So process management is a relevant aspect, relevant for being process engineers or management engineers in particular. Management models are useful for building predictions, or what we may call forecasts, or we may subsequently call scenarios. Typically, the problem of environmental pollution is a management model in which the environmental engineer is faced with the problem of managing pollution sources in order to lowering at most the impact on the ecological system. You shall keep in mind that all these models, all the management models, are all arise from research models. This is why it is important to build research models in a consistent way. An example of this is the DPSIR framework model, that is a conceptual model used to classify environmental indicators. We will see another example of application of a DPSIR framework. The DPSIR framework was introduced by the European Union in the 70s and was used to classify indicators of environmental quality. In particular, D means drivers, P means pressure, state, S, impact I, and R is the response. Typically, driver may be I need to produce food, so agriculture. Pressure is I need to use fertilizer, and state bomb, ditches that is receiving the water flowing on my field is full of nutrients. This changes the state of my system. A lot of nutrient has an impact. You have electrification, and as a response, you may have, for example, the Common Agricultural Practice (CAP), in which the member countries of the European Community are obliged to employ some limitation on the use or on deployment of fertilizer. So models, as we see it, are models are tools for scientific inquiry. For example, Newton's law describes the motion of objects subject to gravitational forces, but all the models are perfectible. For example, Newton's laws does not include friction. So you may always be ready to, how do you say, perfectionate, to improve your model by including more aspects that were neglected in the beginning phase. Models can be made arbitrarily complex, but then you're faced with the problem of resolving the equation, mathematical equation. Models are ready to use tools for describing complex systems. Ecosystems, of course, are very complex systems, complex in the sense I introduced in the beginning. They embrace several hierarchical levels. We need models as a synthesis tool in order to try to synthesize or to make synthesis of our analytical results. Holism, that is an epistemological concept, is an essay of trying to describe the entire system by reducing the detail of individual processes. So from the next lecture on Thursday, we will introduce the concept of holism and reductionism. So are, if you want, different ways of describing or approaching to a description, to the paradigm of natural system. What are the benefits of using models? They allows us to analyze complex systems. They allows us to study the properties of this system. They reveal the limits of our understanding. So this means that they help the scientists to improve their theoretical description. They help the scientists to test scientific hypotheses. In general, when we use models for verifying scientific hypotheses, we may have 4 different cases. The model is correct and the assumption is correct. This almost never happens, but most likely you will have a correct model with wrong assumption and or a wrong model with correct assumption. In the worst case possible, is you may have a wrong model and wrong assumption. So in this case, we suggest that you should change your work. Okay, we stop here today. You should have the possibility of download the handouts from the Moodle pages. You can always write to my email, that is lpalmeri@unipd.it. Please notice that this is slightly different from classical institution. It is name dot surname. For me, but I'm very special, I have L. Palmeri. Please feel free to write me for asking me any clarification or if you have any doubts. Otherwise, I stop here now. I wait for your question. Of course, if you have any question, please ask me. And otherwise, we will meet next Thursday for the next lecture.
Thank you. Bye, Professor.
Bye-bye. If you have any question, I'm here.